Welcome to the debate. Today we are wrestling with a seemingly small but I think profoundly important feature of modern C++, the Noexcept specifier. This keyword, well, it dictates whether a function promises not to propagate exceptions. And its introduction back in C++11 really shifted how we approach both safety and speed. The central question we're tackling is this. Which function? Is it the contractual enforcement of exception safety? Or is it enabling algorithmic efficiency? Which one is the principal driver and really the most critical value of this Noexcept feature?
The central question we're tackling is this. Now, I firmly believe that Noexcept is fundamentally a formal architectural contract. It's there to define and enforce API stability and correctness. And I come at it from a slightly different angle. While I absolutely grant that it's expressed as a contract, I think its purpose for existence, especially in the modern C++ standard library, is almost entirely rooted in unlocking massive optimization. Specifically, those algorithmic performance gains that are just, well, essential for high-performance generic programming these days.
Okay, let's maybe dig into why this contract aspect is so vital. Before Noexcept, the no-throw guarantee, the promise that a function wouldn't throw, was typically, well, it was stuck in the documentation. Maybe a comment above the function signature if you were lucky. It was just a convention, right? Not really a commitment. The real power of Noexcept is that it elevates this essential guarantee into something first class, something machine-checkable, baked right into the function's interface. It codifies expected behavior. It turns a soft rule into a hard requirement, and we absolutely need this kind of formalization for foundational operations. Think about any component that tries to enforce the strong exception guarantee, the commit or rollback semantics. For that guarantee to actually hold up, the components it relies on, like destructors, which are now implicitly Noexcept by default since C++11, or certain internal helper functions, they must be non-throwing. The contract is really the linguistic pillar holding up these safety features. And maybe the most powerful evidence of its contractual nature is, well, what happens if you break it? If an exception does somehow manage to escape a function marked Noexcept, the runtime doesn't try to handle it or unwind the stack in the normal, often high overhead way. Nope. Instead, control is immediately transferred straight to std.terminate. Now, that's a very deliberate, low overhead enforcement mechanism. It's designed specifically to uphold the contract, immediately. It's basically a targeted execution of the program, stopping it from proceeding in some undefined or potentially corrupted state. The compiler knows it doesn't need to bother generating all that complex logic for safe stack unwinding, precisely because the programmer made this explicit promise.
Okay, yeah, that's a compelling case for std determinate acting as the harsh warden of the contract, I suppose. I don't deny its role in enforcement. However, I'd argue that this really harsh enforcement is only necessary because the reward for meeting the contract is so massive, and that reward is the optimization. The raison d'etre, or the reason for including Noexcept in C++11, wasn't just, to make destructors look a bit tidier on paper. It was put there to unlock profound algorithmic performance that compilers simply couldn't safely achieve before. Think about what happens when a function might throw. The compiler has to treat that function as a potential non-local control transfer point that really inhibits aggressive optimization across the call site. The compiler is forced to generate a massive amount of hidden machinery. People often call them landing pads and lookup tables, inserted right into the binary just in case that exception pathway is ever taken. And it bloats the code size, it slows down compilation, and it fundamentally obscures the linear flow graph that the optimizer relies on. So by explicitly declaring a function Noexcept, you are essentially signing an affidavit for the compiler. You're telling it, don't worry about exceptions here. You eliminate the need for all that defensive code generation, and this simplified control flow enables all sorts of conventional but extremely critical optimizations, like more aggressive instruction reordering, better register allocation, and, crucially, inlining. The primary value isn't just the absence of the throw itself. It's the systemic performance gains that come from giving the optimizer a clear, linear path to follow. The contract, in my view, is merely the ticket you need to board the optimization train.
I see why you focus on the compiler hint. That makes sense. But if it were purely about, say, micro-optimization, the feature would probably be less critical overall. Let's move to where this disagreement really sharpens, the whole std.vector dilemma, which for me illustrates precisely why the contract has to come first.
Ah, yes, the std.vector case. I agree, this is key. And for me, the container dilemma is the definitive proof that optimization is primary. So when generic containers like std.vector need to grow, right, they need to resize their internal buffers. They face a choice. They could perform a safe but potentially very slow copy of all the elements into the new buffer. This maintains the strong guarantee, ensuring that if anything goes wrong mid-copy, the original vector remains intact. That's safe, absolutely, but it's O of n performance for the copy operation, slow. Alternatively, if the elements support move semantics, the container can attempt a fast move. Now, this is an algorithmic optimization. It's typically amortized O of 1, a difference that can be, orders of magnitude faster in real-world code. The Noexcept operator provides the exact compile time check the vector implementation needs to choose the optimal path. If the element's move constructor is marked Noexcept, meaning it's non-throwing, standard vector can confidently execute the fast move. That massive performance gain from fast moving, that's the goal. The Noexcept status is just the explicit language-enforced switch that makes achieving that performance goal safely possible.
Okay, that's a strong operational argument, I'll give you that. But let me try and reframe the priorities here. The optimization only becomes permissible, only becomes safe, because the programmer first guarantees the contract. What happens if a move constructor, one that's being used specifically to get that performance boost, actually throws mid-operation?
Right. Bad news.
Exactly. The container completely violates its fundamental invariance. It fails the strong guarantee utterly. Imagine you've got elements split between the old buffer and the partially constructed new one. The std vector is left in an irrevocably corrupted state. You might have dangling pointers, internal size counters mismatched. The whole logical state is just broken. The system can't recover from that reliably.
The contractual no-throw guarantee is the required precondition for enabling performance while maintaining correctness. You absolutely must have that license of correctness, that contractual guarantee, before you can safely chase the speed. So the primary value has to be the foundational guarantee of correctness, which the contract provides, making the high-speed move a safe option in the first place. I absolutely agree that correctness is paramount. Nobody wants corrupted vectors. But the language feature, Noexcept, was designed specifically to bridge that performance safety gap created by move semantics. If move operations were somehow intrinsically safe without needing the contract, well, we wouldn't need Noexcept at all, would we? Its purpose is precisely to leverage the fast move while simultaneously mitigating the exact disaster scenario you just described. You could almost see it as a risk management tool applied specifically for performance reasons. And if we look at the other end of the optimization spectrum, local micro-optimizations, we actually see that the contract isn't always needed purely for performance. For many simple, small functions, modern compilers are actually quite smart. They can often perform flow analysis and deduce for themselves that no exception can possibly be thrown. In these cases, the compiler often applies the same micro-optimizations, omitting those landing pads, doing aggressive inlining, even without an explicit Noexcept specifier from the programmer.
That's an interesting point about compiler deduction, yeah. And one that actually, I think, strengthens my argument for the contract. The very fact that the compiler can sometimes deduce exception status for simple functions suggests that, for mere performance hints on small things, the specifier can indeed be redundant sometimes. But the contract remains absolutely necessary for API robustness and clarity, especially in layered abstractions. The real power of Noexcept here lies in its reflective capability, the Noexcept operator. Now, this is the critical feature.
It allows generic templates, like our std.vector, to programmatically query the guarantees of underlying types at compile time. This capability for static contract reflection is just essential for composable software design. It lets us propagate safety guarantees up the entire call chain, and that's completely independent of whether it provides a local performance hint or not.
It defines the interface publicly and checkably.
That reflection capability is powerful. Yes, I won't argue that. But let's be pragmatic about how it's actually used. It is overwhelmingly leveraged precisely for those systemic challenges, like the std.vector dilemma, where the compiler needs that explicit guarantee to make a crucial algorithmic choice, move versus copy. The contract's utility in practice seems functional only insofar as it enables that performance-critical decision. When you're writing a standard library feature or any high-performance generic code, you are driven by the requirement to provide the fastest, safe implementation possible. That's fundamentally an optimization mandate. I'm just not convinced that the simple declaration of the contract is the principal driver in its own right. In fact, the permanence you mentioned earlier, the sort of high stakes involved in applying Noexcept, actually exposes a limitation that, for me, proves performance intent is what truly motivates its usage.
Wait, I thought the high stakes underscored the contract's foundational role. Applying Noexcept to a public API function is a permanent, high-stakes commitment. You can't easily take it back later without breaking clients, right? Because those clients, including template libraries, may well have relied on that promise, maybe by using the Noexcept operator query. This permanence dictates the stability and reliability of the entire system structure built upon it. It is, almost by definition, a contractual pillar. How is that not about the contract first?
Okay, I agree on the permanence aspect. It is a strong commitment. But that commitment is often conflated, perhaps unconsciously, by the programmer with a much stronger no-fail guarantee that the language itself does not actually enforce. And this is where the intent, I believe, shifts decisively toward performance enablement. Remember, the feature only guarantees no throw. That's it. A function can be marked Noexcept, but still fail its logical operation. Think of, say, a resource allocation attempt that returns a null pointer, or maybe it hits some internal logic error. It doesn't throw, but it certainly didn't succeed. It might leave the object in a valid, but perhaps unusable state. That still meets the letter of the Noexcept language contract, but it clearly violates the semantic expectation most programmers have when they rely on something like a move operation for correctness in a container. So, when a programmer marks a move constructor Noexcept, they are implicitly making that stronger, uncheckable semantic promise that the move will actually succeed, the no-fail interpretation, you might call it, which is absolutely necessary for the container optimization to work safely and correctly. The true underlying contractual responsibility relies on programmer discipline to ensure success, all in order to enable the desired performance outcome. This, to me, shows that the optimization intent drives the usage. The language mechanism just enforces the bare minimum no-throw part of the overall promise needed to make that performance possible.
You are highlighting an important distinction there, that the language contract is only about exception propagation, not semantic success. But, well, that simply means the programmer has to be careful not to conflate the two. The language contract itself is clear. No exceptions propagate, period. If the system, like std.vector, relies on that explicit, checkable promise to enable a safe, high-speed move, then the Noexcept contract is absolutely fundamental to maintaining program correctness while utilizing that performance path. It defines the required exception safety guarantee. It transforms API specification from, mere documentation into machine-checkable code. And through that, we prioritize program correctness and system composability by formalizing the no-throw guarantee.
And I maintain that the feature's very existence is driven by necessity. The necessity to bridge that gap between high-performance features like move semantics and robust exception safety. It provides the critical switch, the permission slip, if you will, necessary to achieve significant algorithmic efficiency in generic libraries. Look, if pure contractual signaling were the only goal, maybe a simple runtime check that just calls the logging function if something unexpectedly throws would have sufficed. The harsh, irreversible action of std terminate is what makes the optimization safe to apply. It reinforces that the core intent is enabling performance, secured by a rather fatal contract.
Well, it's certainly clear we both agree that Noexcept exhibits a profound and really necessary symbiotic relationship. It's the mechanism that allows programmers to essentially trade away the flexibility of reporting errors via exceptions in exchange for a critical guarantee of safety and, ultimately, as you point out, speed.
Precisely. Yes, symbiotic is a good word. It's the linchpin connecting high-performance generic programming with strong safety guarantees. It requires the programmer to make a pretty solemn, high-stakes commitment to non-throwing behavior in order to achieve the kind of speed that modern C++ applications often demand.
So we'll leave it to our listeners to consider which function, the foundational contract ensuring system correctness and composability, or the resulting algorithmic performance gains it crucially unlocks, they believe represents the feature's ultimate principal driver in modern C++.